So here we have a certain fraction of electrons that can wander around. What's going to happen that the electrons want to be attracted by these positive charges. Plus and minus attract each other. And so some of these electrons which can freely move will move in this direction, and so the plus charges stay behind. This process we call induction. You get sort of a polarization. You get a charge division. It's a very small effect. Perhaps only 1 in 10 to the 13 electrons that was originally here will end up here, but that's all it takes. So we get a polarization, and we get a little bit more negative charge on the right side than we have on the left side. And so what's going to happen is, since the attraction between these two will be stronger than the repelling force between these two, because the distance is smaller, and Franklin had already noticed, the shorter the distance, the stronger the force. What will happen is that if this object is free to move, it will move towards this rod. And this is the first thing that I would like you to see. I have here a conductor. It is a balloon, helium-filled balloon. And I will rub this rod with silk. And as I approach that balloon, you will see that the balloon comes to the rod. I will then try to rub with that rod several times on that balloon. It will take a while, perhaps, because the rod itself is a very good non-conductor. It's not so easy to get charge exchange between the two. But if I do it long enough, I can certainly make that balloon positive. Then they're both positive, and then they will repel each other. But first, the induction part, whereby you will see the balloon come to the glass rod. These experiments work best when it is dry in the winter. They don't work so well when it is humid. So it's a good time to teach 802 in the winter. Okay, there we go. This should be positively charged now. And the balloon wants to come to the glass. You see that very clearly? Come on, baby. Okay, so now I will try to get this balloon charged a little. So there is a change of electrons that go from the balloon to the glass. And the glass doesn't, it's not a conductor itself, so it is not always so easy to get charge exchanges. Okay, let's see whether I have succeeded now in making the balloon positively charged as well as the glass rod. If that's the case, then the balloon is not going to like me. The balloon will now be repelled. And you see that very clearly. To show you now that there are indeed two different kinds of electricity, if I now rub with cat fur, by tradition we do that with cat fur, I don't know why, by tradition we use silk for the glass. So if we do this with cat fur now, then this becomes negatively charged. Remember, there were two types of electricity, and since that balloon is positively charged, now the balloon will come to me. And there it is. Now it comes to me. So you've seen for the first time now clearly that there are two different kinds of electricity. The positive charge is chosen by Franklin on the glass rod, and the negative charge on the rubber. So now you may think that if I approach a non-conducting balloon with a glass rod, and I have a non-conducting balloon here, you may think now that this balloon will not come to the glass rod because there are no free electrons. So these electrons cannot freely move, and so you don't get this polarization, you don't get this induction. But that is not the case. And this is actually quite subtle. You have to look now at the atomic scale. If I take an atom like you have here, you have positive charge, and you have the electrons here in a cloud around the positive nucleus. If I bring a glass rod, positively charged nearby, then these electrons, which are stuck to the atoms, they cannot freely move like in conductors, however, will spend a little bit more time on the side where the glass rod is, because they feel attracted by the glass rod, whereas the nuclei, if anything, want to go away from the glass rod. So what you're going to see is that, in a way, if I started off with a spherical atom, let's suppose this were a spherical atom or a spherical molecule, then what will happen is that you get sort of a shape like this, and the electrons spend a little bit more time here than they spend here, and that means that I have actually polarized that atom. If the electrons spend more time on this side of the atom than on this side, I have also created the phenomenon of induction, and I therefore expect that this side becomes more negative than that side. And I can show you that in a nice way with a transparency, whereby I have plus and minus signs, and I have equal number of plus and minus signs. So they represent neutral atoms. There you see them. Boy, it's a little dirty, but maybe see I can clean it a little. Okay. Okay. So here we go. So notice there are equal amount of pluses and minuses. So think of the plus and the minuses as one neutral atom, just a representation. Now I'm holding a glass rod on this side, which is positively charged. And so each atom, the electrons want to go a little bit to this side, and so the nucleus stays behind. And if each atom does that, this is what's going to happen. And now notice what you end up with. In the middle of the substance, plus and minuses cancel each other out again. But on the right side, you have created a negatively charged layer, and on the left side, you have created a positively charged layer. And so in a way, you have again induction. So even in the non-conducting objects, this side will turn negative, and this side will turn positive. And therefore, if I approach a non-conducting balloon with a glass rod, I will also see the balloon come to me. And so I can easily show you that. It doesn't make any difference whether I choose glass or whether I choose rubber. I can do it with both. Non-conducting balloons always have a potential problem. The potential problem is that